Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Our universe beckons with destinations beyond imagination, yet the vast gulfs between stars present humanity with its greatest challenge. As we stand on the precipice of becoming an interplanetary species, we face a fundamental problem. The human body was not designed for the timescales of deep space travel. A journey to our nearest stellar neighbor, Proxima Centauri, would take over 4 years at light speed, a velocity far beyond our current technological reach. At achievable speeds, such journeys would span decades or centuries, exceeding a human lifetime. Nature, however, has already solved this problem. Throughout Earth's ecosystems, creatures from bears to frogs employ biological mechanisms that could hold the key to our interstellar future: hibernation. By drastically reducing metabolic rates, these animals survive extended periods without food or water, while simultaneously preserving muscle mass and cognitive function. This natural blueprint has inspired one of space exploration's most promising frontiers: human hibernation technology. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The European Space Agency's advanced concepts team formally recognized hibernation's potential in 2019, establishing the first dedicated research program investigating its application for crewed Mars missions. NASA followed in 2021, launching the biological Stasis Research Initiative. These weren't flights of fancy, but calculated responses to mounting challenges in life support, psychology, and radiation protection during extended space missions. What exactly happens during hibernation? In natural hibernators, body temperature drops dramatically. A black bear's core temperature decreases by 5 to 9 degrees Celsius. Heart rate slows from 50 beats per minute to as few as 10. Oxygen consumption and metabolic activity decrease by up to 95%. Most remarkably, hibernators experience minimal muscle atrophy despite months of inactivity, a phenomenon scientists call protein conservation that defies our understanding of human physiology. The benefits for space travel would be transformative. Resource consumption would decrease exponentially. A hibernating crew would require 80% less food and water. Waste production would diminish proportionately. Psychological challenges of extended isolation would be mitigated through reduced conscious time. Perhaps most significantly, preliminary research suggests that the slowed metabolism might provide ancillary protection against cosmic radiation damage, potentially addressing space travel's most pernicious health risk. Hibernation isn't suspended. Animation from science fiction, explains Dr. Jennifer Alvarado, lead researcher at NASA's Biological Stasis Research Initiative. It's a carefully regulated physiological state that evolved naturally on Earth. We're not freezing people. We're inducing a profound metabolic suppression that the body is inherently capable of entering under specific conditions. The challenges remain substantial. Humans lack the genetic programming for natural hibernation. Our bodies actively resist hypothermia, employ shivering mechanisms to maintain temperature, and suffer rapid muscle atrophy during inactivity. However, recent breakthroughs in neurochemistry, genetic research, and pharmaceutical science have opened promising pathways toward human hibernation that seemed impossible just a decade ago. Most significantly, the discovery of the hibernation induction trigger, a complex of chemicals found in hibernators' blood, has provided researchers with a potential key to unlocking this dormant capability in humans. As we stand at this technological frontier, one question looms: how close are we to making human hibernation a reality for space exploration? The answer lies in understanding both the remarkable progress already achieved and the formidable challenges that remain. The quest to develop human hibernation began with extensive studies of natural hibernators, from the Arctic ground squirrel with its near-freezing body temperature to the fat-tailed dwarf lemur, our closest hibernating evolutionary relative. These animals aren't simply sleeping. They enter a physiological state called torpor, characterized by precisely regulated metabolic suppression that can reduce energy requirements by up to 98%. The Arctic ground squirrel represents nature's extreme case. During winter hibernation, these remarkable creatures maintain body temperatures just above freezing, as low as -2 degrees Celsius, without experiencing tissue damage. Their heart rates drop from 200 beats per minute to under C10. Most impressively, they cycle through torpor phases lasting 2 to 3 weeks, briefly warming themselves every 12 to 25 days in a controlled process called interboot arousal. What makes this possible is an intricate cascade of molecular signals, explains Dr. Matteo Cerri, neurophysiologist at the University of Bologna. Hibernation isn't controlled by a single gene or protein, but by complex neurological and endocrine pathways that systematically reorganize the animal's entire metabolism. The breakthrough came in 2022 when researchers at the University of Alaska identified adenosine A1 receptor agonists as key facilitators of torpor induction. These compounds effectively switch off thermoregulation in the central nervous system, allowing body temperature to drop without triggering emergency countermeasures. Simultaneously, teams at Harvard Medical School isolated specific microRNAs that regulate protein synthesis during hibernation, explaining how muscle mass remains preserved despite prolonged inactivity. These discoveries led to the first successful induced torpor in non-hibernating mammals. In 2023, researchers at Tokyo Medical University maintained laboratory rats in a hibernation-like state for 72 hours using a synthetic compound that mimics natural hibernation trigger molecules. The animals experienced a 60% reduction in metabolic rate with no apparent adverse effects upon awakening. Human applications followed swiftly. The European Space Agency's Advanced Concepts team made headlines in 2024 by inducing a shallow torpor state in human subjects during a controlled medical trial. 6 volunteers maintained a 3 degrees Celsius reduction in core body temperature for 48 hours, with corresponding 35% decrease in metabolic rate. This wasn't true hibernation, cautions Dr. Bradford Wilkins, medical director of the European Space Agency's study, but it demonstrated that human physiology can safely enter a hypothermic, hypermetabolic state under controlled conditions without triggering catastrophic thermoregulatory responses. Perhaps the most promising development comes from the field of synthetic biology. The SpaceX-funded Hibernation Research Consortium announced in early 2024 the successful CRISPR-based integration of key hibernation-associated genes from the 13-lined ground squirrel into human cell lines. These modified cells demonstrated remarkable resistance to cold shock and reduced energy consumption when exposed to hibernation-inducing factors. Pharmaceutical approaches have yielded equally impressive results. A team at Massachusetts General Hospital developed a drug cocktail nicknamed Winter Bear that temporarily suppresses the hypothalamus's temperature regulation while activating adenosine pathways throughout the body. Human clinical trials using modest doses achieved a 20% reduction in metabolic rate without requiring external cooling, the first demonstration of pharmaceutical torpor induction in humans. The medical applications extend beyond space travel. These same technologies show promise for emergency medicine, where induced hypothermia already saves lives after cardiac arrest by reducing brain oxygen requirements. Expanded capabilities for metabolic suppression could revolutionize trauma care, organ transplantation, and treatment of ischemic conditions. Despite these advances, full human hibernation remains aspirational. The most significant hurdle isn't initiating torpor, but maintaining it safely for extended periods. Natural hibernators possess specialized cellular mechanisms to prevent blood clotting, preserve neural connections, and protect against oxidative damage during months of torpor, adaptations humans naturally lack. Creating medical workarounds for these limitations represents the research frontier. As Dr. Jennifer Alvarado notes, we're not trying to simply copy what bears do, we're developing a human-optimized approach to metabolic suppression that incorporates both biological inspiration and technological innovation. Transforming hibernation from laboratory experiment to practical space travel technology requires sophisticated life support systems specifically designed for long-term metabolic suppression. The hibernation pods being developed by NASA's Biological Stasis Research Initiative bear little resemblance to the coffin-like chambers depicted in science fiction films. "We're designing comprehensive medical environments," explains Dr. Marcus Chen, Chief Engineer at NASA's Advanced Exploration Systems Division. These hibernation systems must monitor and regulate dozens of physiological parameters simultaneously while maintaining redundant life support capabilities for months or years of continuous operation. The current generation of hibernation pods, developed jointly by NASA and SpaceX, resembles advanced medical beds enclosed within cylindrical chambers approximately 2.5 meters long and 1 meter in diameter. These units integrate multiple subsystems, precision temperature regulation, capable of maintaining body temperature within 0.01 degrees Celsius, continuous physiological monitoring through non-invasive sensors, automated drug delivery systems, waste management, nutrition administration, muscle stimulation arrays, and countermeasures against bone density loss. Temperature management represents a primary engineering challenge. Human hibernation requires core body temperature reduction to approximately 32 degrees Celsius, cold enough to suppress metabolism, but not so cold as to trigger tissue damage or coagulation disorders. The pods achieve this through direct contact cooling, carefully regulated air temperature, and internal circulation of temperature-controlled fluids through specialized garments worn by the hibernator. The cooling process takes approximately 6 hours, says Dr. Elena Rodriguez, Medical Director for NASA's hibernation trials. "We induce torpor pharmacologically first, then gradually reduce body temperature, while continuously monitoring brainwave patterns and metabolic markers to ensure the process remains within safety parameters." Muscle atrophy prevention has proven particularly challenging. Natural hibernators possess genetic mechanisms that preserve muscle mass despite months of inactivity, adaptations humans lack. Engineers have addressed this through programmable electrical muscle stimulation systems built into the hibernation pods. These generate carefully calibrated contractions in major muscle groups without disrupting torpor, providing sufficient stimulation to prevent atrophy while minimizing energy expenditure. Nutrition delivery occurs through specialized feeding solutions, administered intravenously or through nasogastric tubes. These formulations contain precisely calibrated macronutrients, micronutrients, and pharmaceutical agents that support cellular maintenance during torpor while requiring minimal digestive processing. The current generation can sustain a hibernating human for up to 8 months without external replenishment. Medical monitoring incorporates artificial intelligence systems trained specifically on hibernation physiology. These constantly analyze thousands of data points, identifying patterns that might indicate emerging complications hours or days before they become critical. 2 independent AI systems cross-check each other's assessments, with disagreements, triggering human medical review via distant Earth communication or awakening of onboard medical personnel. The most challenging aspect is the awakening process, notes Dr. Rodriguez. Rewarming must occur gradually, no faster than 0.5 degrees Celsius per hour, while carefully managing fluid balance, electrolyte levels, and cardiovascular function. Natural hibernators possess specialized proteins that prevent reperfusion injury during arousal. We've developed pharmaceutical analogs of these compounds, but awakening remains the highest risk phase of the hibernation cycle. Deep space missions would likely employ hibernation in rotational shifts rather than placing the entire crew in torpor simultaneously. This approach ensures continuous human oversight while still achieving significant resource conservation. A typical Mars mission profile might maintain 2 crew members awake, with 4 in hibernation, rotating every 2 months to distribute hibernation periods equitably among the crew. Radiation protection has emerged as an unexpected benefit of hibernation. Technology. While early researchers worried that unconscious crew would have increased vulnerability to cosmic radiation, experimental evidence has revealed the opposite. The reduced metabolic rate of hibernation appears to enhance cellular repair mechanisms while decreasing oxidative stress from radiation exposure. SpaceX's 2023 sleeping mouse experiment on the International Space Station found that hibernating mice experienced 40% less DNA damage from cosmic radiation compared to active controls. As these systems advance, their applications extend beyond space travel. The medical community has already adopted modified versions of hibernation technology for emergency medicine, organ transplantation, and treatment of traumatic injuries. Military research programs are exploring hibernation for medical evacuation from remote locations, potentially extending the golden hour for trauma treatment to days or weeks. The psychological implications of long-term hibernation represent one of the technology's most profound aspects, and potentially its greatest unknown. Natural hibernators experience dramatic changes in brain activity during torpor. Electroencephalogram. Readings from hibernating ground squirrels show patterns unlike anything seen in normal sleep, with neural activity reduced to levels that would indicate severe brain damage in actively metabolizing animals. Yet these creatures awaken with cognition fully intact, memory preserved, and behavior patterns unchanged. This challenges our fundamental understanding of consciousness and memory formation, explains Dr. Sophia Nakamura, neuropsychologist at the SETI Institute's Human Factors Division. Hibernators are demonstrating that consciousness can be effectively paused and resumed without information loss, something we previously thought impossible based on our understanding of human cognition. The initial concern among researchers was that human hibernation might cause catastrophic memory loss or personality changes. Animal studies indicated that hibernation suppresses the hippocampus, the brain region responsible for memory consolidation, to near zero activity levels. How then could memories formed before hibernation survive months of neural dormancy? The answer appears to lie in structural protein preservation. During normal metabolism, memories become encoded through physical changes to synaptic connections. Hibernators possess specialized molecular mechanisms that stabilize these physical neural structures during torpor. Early human hibernation trials experienced memory complications until researchers developed the neurostabilizing compound NSC214, which mimics these natural preservation mechanisms. We now routinely achieve complete memory preservation across hibernation cycles, reports Dr. Yusuf Al-Farsi, lead investigator for NASA's Cognitive Preservation Protocol. Subjects can enter hibernation mid-conversation and resume their exact train of thought upon awakening 3 months later. It's as if their conscious experience picks up precisely where it left off, with the intervening time simply absent rather than forgotten. This phenomenon has fascinated philosophers as much as scientists. If subjective experience effectively pauses during hibernation, does the hibernator experience the passage of time? Interviews with participants in extended hibernation trials suggest they do not. One participant in a 90-day hibernation study reported the experience as closing my eyes for what felt like seconds, then opening them to discover 3 months had passed. This raises intriguing possibilities for the subjective experience of interstellar travelers, who might experience journeys of decades or centuries as mere moments of personal time. Pre-hibernation psychological preparation has emerged as critically important. Early trials revealed that subjects inadequately prepared for the experience of time skipping often experienced profound disorientation upon awakening. Current protocols include extensive virtual reality simulations of the awakening process, psychological conditioning to reduce temporal disorientation, and careful management of the hibernation environment to provide subtle cues about elapsed time. Dream studies during hibernation have yielded unexpected insights. While natural hibernators show minimal REM sleep patterns during torpor, human subjects report vivid dreaming experiences despite EEG patterns showing suppressed neural activity. These dreams often have distinct characteristics: slower pacing, enhanced problem-solving elements, and unusual temporal properties, suggesting a fundamentally different mode of consciousness than normal sleep dreaming. I believe the brain enters a unique energy conservation mode during hibernation. explains Dr. Nakamura. Rather than shutting down completely, it shifts to an extraordinarily efficient processing state that maintains essential cognitive functions while minimizing energy expenditure. These hibernation-specific dream states may represent the minimum viable activity needed to maintain neural network integrity. For deep space missions, hibernation offers significant psychological benefits. Beyond resource conservation, extended periods of consciousness in the confined environment of a spacecraft create substantial psychological strain, contributing to conditions like depression, anxiety, and interpersonal conflict. Hibernation effectively reduces subjective mission duration from the crew's perspective, potentially mitigating these stresses. A Mars transit mission might last 9 months objectively, notes Dr. Alfasi, but with rotational hibernation, each crew member might only experience 3 months of conscious time. This dramatically reduces the psychological burden of confinement and isolation. Some researchers have proposed more radical applications, suggesting that hibernation technology might allow voyages spanning centuries of objective time, while subjectively aging crew members only months or years. Such approaches would require solving additional technical challenges related to extremely long-term life support, but could theoretically enable human exploration beyond our solar system without requiring faster-than-light travel technology. The question remains, how will humans psychologically process the experience of crossing vast distances while subjectively experiencing almost none of the journey? This unprecedented disconnection between objective and subjective time represents uncharted territory for human psychology. The practical implementation of hibernation technology for space exploration requires comprehensive redesign of spacecraft architecture. Traditional human-rated spacecraft dedicate approximately 60% of their mass to life support systems, crew quarters, and consumables. A hibernation-capable vessel dramatically redistributes these allocations, potentially revolutionizing mission profiles for destinations throughout our solar system. Hibernation changes everything about spacecraft design, explains Dr. Hiroshi Yamamoto, Chief Mission Architect at JAXA, the Japanese space agency. When crew members spend 80% of their mission in torpor, you no longer need extensive habitation modules, recreational facilities, or daily consumable storage. This mass can be redirected toward propulsion, scientific equipment, or mission redundancy systems. NASA's proposed Mars Deep Sleep Transit Vehicle illustrates these principles. Designed to carry 6 astronauts to Mars using rotational hibernation, the spacecraft is approximately 40% smaller than equivalent non-hibernation designs. The habitation module accommodates only 2 active crew members, with the remaining 4 in hibernation pods housed in a separate, minimal-volume torpor chamber. This configuration reduces launch mass by an estimated 37% compared to conventional designs. The mass savings translate directly into mission capabilities. Reduced life support requirements mean smaller solar arrays, less radiator, surface area, and decreased power storage needs. This cascading effect ultimately enables either faster transit times through additional propellant allocation or expanded scientific payload capacity. The deep sleep architecture allows a 25-ton scientific payload, nearly triple the capacity of traditional mission profiles. Life support systems for hibernation vessels employ closed-loop recycling technologies optimized for extremely high reliability rather than processing capacity. Since active crew numbers remain minimal, these systems can be smaller, while incorporating multiple redundant components to ensure uninterrupted operation throughout the mission duration. The engineering challenge shifts from capacity to longevity, totes Dr. Elena Kuznetsova, life support systems engineer at the European Space Agency. Traditional designs must process large volumes of water, air, and waste daily. Hibernation vessels process much smaller volumes, but must maintain flawless operation for years without maintenance opportunities. Radiation shielding represents a particular engineering challenge for deep space missions. Without Earth's protective magnetosphere, astronauts face continuous exposure to galactic cosmic rays and unpredictable solar particle events. Hibernation offers two complementary advantages: reduced consciousness during the highest radiation exposure periods of transit and enhanced cellular repair mechanisms during torpor that mitigate radiation damage. JAXA's Artemis Deep Space Habitat demonstrator, scheduled for lunar deployment in 2026, will test these principles in cislunar space. The module includes 3 hibernation pods and a comprehensive radiation monitoring system to quantify the protective effects of torpor against actual deep space radiation conditions beyond Earth's magnetosphere. Power systems for hibernation vessels favor reliability over peak capacity. Since hibernation pods consume relatively little energy, approximately 300 watts per occupied pod, spacecraft can operate on modest solar arrays even at Mars distances from the Sun. However, these systems must function flawlessly for years without human intervention, necessitating new standards for component longevity and automated fault detection. The first likely application will be NASA and SpaceX's proposed Mars Hibernation Pathfinder mission, tentatively scheduled for the 2030 Mars transit window. This pioneering mission would place 4 astronauts in rotational hibernation for the transit phases to and from Mars, with full crew activation during the 3-month surface exploration phase. The mission architecture demonstrates hibernation's transformative potential, enabling a full Mars surface mission with a spacecraft approximately 55% the mass of conventional designs. Hibernation doesn't just make Mars missions more efficient, it makes them more humane, says Dr. Yamamoto. By reducing transit consciousness, we maximize the proportion of mission time spent actually exploring Mars rather than simply traveling there and back. This fundamentally changes the cost-benefit analysis of human planetary exploration. Beyond Mars, hibernation becomes not merely advantageous, but potentially enabling for human exploration of the outer solar system. A conventional mission to Jupiter's moon Europa would require approximately 6 years round trip, using chemical propulsion, a duration that creates nearly insurmountable challenges for psychological health and life support reliability. With hibernation, such a mission becomes feasible within existing technological constraints. The European Space Agency and Roscosmos have jointly proposed the Europa Hibernation Explorer concept, a 36-month mission that would maintain its 6-person crew in hibernation, except for 2 one-month active periods, during Jupiter orbital insertion and during Europa proximity operations. This approach reduces the subjective mission duration to just 2 months, despite the 36-month objective timeline, potentially enabling human exploration of the outer planets within a single professional astronaut's career span. While human hibernation offers compelling advantages for solar system exploration, its transformative potential becomes truly apparent when considering interstellar missions. Even our nearest stellar neighbor, Proxima Centauri, lies 4.2 light-years away, a distance that would require decades to traverse using foreseeable propulsion technologies. Without some form of suspended animation, sending humans to other stars would demand either multi-generational spacecraft or crew lifespans far exceeding current capabilities. Interstellar hibernation creates a bridge between our current technological reality and our aspirations to reach other stars, explains Dr. Yuan Chen, astrobiologist and interstellar mission architect at NASA's Jet Propulsion Laboratory. It transforms missions spanning decades into subjective experiences lasting months or years, bringing interstellar exploration within the psychological horizon of individual human experience. The Breakthrough Starshot initiative, initially focused on sending gram-sized probes to Proxima Centauri using laser-driven light sails, has recently established a parallel research track examining hibernation technologies for potential crewed missions. While the miniaturized probes might reach 20% of light speed through laser propulsion, larger crewed vehicles would likely achieve no more than 10 to 15% of light speed using foreseeable fusion propulsion systems. At such velocities, a journey to Proxima Centauri would require approximately 30 years of transit time. Without hibernation, this presents insurmountable challenges for consumable storage, psychological health, and crew lifetime limitations. With advanced hibernation, however, crew members might experience the journey subjectively as months rather than decades. The mathematics of interstellar travel fundamentally change when you incorporate hibernation, notes Dr. Fatima Al-Zahra, theoretical physicist at the European Space Agency's Advanced Concepts team. Resource requirements no longer scale linearly with objective mission duration, but rather with subjective, experienced time. This effectively extends our practical exploration radius by an order of magnitude. Hibernation technology for interstellar applications would require significant advances beyond current capabilities. While today's experimental systems can safely maintain torpor for months, interstellar missions would demand hibernation periods spanning decades with complete reliability. Current research focuses on three approaches to this challenge: metabolic, stasis, synthetic biological enhancements, and partial cybernetic integration. Metabolic stasis represents the most conservative approach, essentially extending current pharmaceutical and environmental hibernation techniques to longer durations. Researchers at the University of California Mars and Exoplanet Research Institute have maintained mice in artificial torpor for 14 months, approaching the current biological record holders like the Arctic ground squirrel that hibernate naturally for 8 months annually. Synthetic biological enhancements offer more radical possibilities. The Hibernation Research Consortium has demonstrated that human cells incorporating certain genes from natural hibernators show dramatically enhanced resistance to metabolic stasis complications. These modified cells maintain membrane integrity during prolonged cold storage and resist the accumulation of toxic metabolites that normally limit hibernation duration. We're not talking about creating genetically modified astronauts, clarifies Dr. Chen. Rather, we're developing therapeutic genetic interventions similar to current gene therapies, temporary modifications that enhance natural human capabilities for specific mission requirements. The most speculative approach involves partial cybernetic integration, using technological systems to maintain critical biological functions during ultra-long hibernation. Theoretical proposals include nanoscale cellular maintenance systems, artificial circulation support, and direct technological interfaces with neural tissue to prevent degradation during decades-long torpor states. These approaches converge with other emerging technologies essential for interstellar exploration. Advanced artificial intelligence would monitor hibernating crew throughout the decades-long voyage. Robotics would maintain spacecraft systems while humans remain dormant. Synthetic biology would support closed ecological life support systems, capable of operating autonomously for decades. We're witnessing the emergence of a technological ecosystem specifically adapted for deep space exploration, observes Dr. Al-Zahra. These distinct technological domains, hibernation, artificial intelligence, advanced robotics, synthetic biology, are independently developing in ways that complement each other for space applications. The first practical test of long duration, hibernation may come sooner than interstellar missions. NASA's proposed Kuiper Belt Explorer would send humans beyond Neptune to study these distant solar system objects, requiring a mission duration of approximately 15 years. By maintaining the crew in hibernation, except during planetary encounters and scientific observations, the mission could reduce subjective experience time to less than 2 years. This mission, tentatively proposed for launch in the 2040s, would serve as the ultimate proof of concept for hibernation technology, potentially clearing the path for truly interstellar missions in the latter half of this century. If successful, it would demonstrate that the fundamental barrier of biological lifespan need not constrain our exploration of the cosmos. As Dr. Chen reflects, throughout human history, our exploration horizons have been limited by the practical constraints of our biology. How far we could walk in a day, how long we could sail without fresh provisions, how many years we could dedicate to a single journey. Hibernation technology promises to finally decouple our exploration potential from these biological limitations. As hibernation technology advances from theoretical concept toward practical implementation, it raises profound ethical questions that extend far beyond engineering considerations. The ability to effectively pause human consciousness for extended, periods challenges our understanding of personhood, consent, duty of care, and the very nature of human experience. These questions demand thoughtful consideration before hibernation becomes operational reality. We're entering uncharted ethical territory, acknowledges Dr. Maya Patel, bioethicist at the Georgetown University Center for Clinical Bioethics and advisor to NASA's hibernation program. When we place someone in torpor for months or years, we're making decisions that profoundly affect their relationship with time itself, decisions that neither medical ethics nor space exploration ethics has previously needed to address. Informed consent presents the first major ethical challenge. How can individuals meaningfully consent to experiences utterly beyond current human experience? NASA's hibernation research protocols require extensive psychological evaluation and comprehensive education about both known and theoretical risks. Yet questions remain about whether genuine informed consent is possible for such unprecedented experiences. This concern becomes particularly acute when considering potential interstellar applications where hibernation might extend for decades. Can an individual in 2025 truly comprehend and consent to awakening in 2075, potentially in a radically different social and technological context? Some ethicists have proposed rolling consent protocols, where long-duration hibernators would be periodically awakened to reassess their continued participation. The concept of duty of care takes on new dimensions with hibernation. Traditional medical ethics establishes clear obligations toward unconscious patients, but these frameworks assume relatively brief periods of unconsciousness with continuous professional monitoring. Hibernation potentially creates scenarios where individuals remain unconscious for years, with only automated or artificial intelligence oversight. The standard of care must evolve to address these unprecedented timeframes, explains Dr. Patel. We're developing ethical frameworks specifically addressing the obligations of mission controllers, medical teams, and artificial intelligence systems toward hibernating individuals over extended durations. Resource allocation ethics presents equally challenging questions. If life-threatening emergencies occur during deep space missions with limited medical resources, how should treatment priorities be established between active and hibernating crew members? The European Space Agency's Hibernation Ethics Working Group has proposed frameworks based on potential consciousness recovery, rather than current consciousness state, a significant departure from traditional triage protocols. Perhaps the most profound ethical questions concern the nature of human temporal experience itself. If hibernation allows an individual to subjectively skip decades while remaining biologically young, it creates unprecedented disconnection between chronological time, biological time, and subjectively experienced time. This raises complex questions about intergenerational responsibility and social continuity. A hibernation-capable civilization might develop distinct temporal classes, suggests Dr. Thomas Okoro, philosopher of technology at the Oxford Future of Humanity Institute. Some individuals might experience time continuously, while others experience it discontinuously through hibernation. This could fundamentally alter social structures, familial relationships, and even the concept of shared cultural experience. These philosophical dimensions extend to our conception of death itself. As Dr. Okoro observes, hibernation occupies an intriguing middle ground between life and death, a state where biological processes continue at minimal levels while conscious experience ceases entirely. This challenges our binary thinking about existence and raises questions about whether other states between full life and complete death might be possible. Religious perspectives on hibernation vary widely. Some theological traditions express concern about technological interference with natural lifespans, while others see hibernation as an extension of medical care consistent with preserving divinely granted life. The Vatican's Pontifical Academy for Life issued a statement in 2023, conditionally supporting hibernation research while emphasizing the importance of maintaining human dignity throughout the process. The legal status of hibernating individuals presents practical challenges requiring resolution before operational deployment. Are hibernating individuals legally deceased, temporarily incapacitated, or something entirely different? How should their property rights, voting rights, and legal responsibilities be managed during prolonged torpor? Several spacefaring nations have begun developing legal frameworks specifically addressing these questions, with Japan's Space Activities Hibernation Act of 2024 establishing the first comprehensive legal structure for hibernating astronauts' rights and responsibilities. Despite these complex questions, most ethicists and philosophers emphasize that hibernation technology itself remains ethically neutral. Its implications depend entirely on implementation choices and governance frameworks. With appropriate ethical guardrails, hibernation offers humanity unprecedented opportunities to explore beyond current limitations. Throughout history, transformative technologies have challenged existing ethical frameworks, notes Dr. Patel. The ethical questions surrounding hibernation aren't reasons to avoid its development, but rather calls to develop it thoughtfully, with full awareness of its profound implications for human experience. As we stand at the threshold of becoming a multiplanetary species, hibernation technology offers a bridge between our biological limitations and our cosmic aspirations. By carefully navigating its technical challenges and thoughtfully addressing its ethical dimensions, humanity may soon embark on journeys that previous generations could only imagine, carrying our consciousness to the stars, one hibernation cycle at a time.